The research paper presents a novel method for modeling the power generation of a fleet of photovoltaic (PV) systems using a smooth periodic Gaussian copula. This approach captures diurnal variation in the distribution of power output, dependencies among different PV systems, and dependencies across time. The method consists of three invertible transformations that map the power from each system to a scalar Gaussian, resulting in a joint probability model of PV fleet output across systems and time. The paper discusses the fitting of a smooth periodic model, applying an autoregressive AR model to account for dependencies across time, and finally fitting a smooth periodic Gaussian distribution to the residual of the AR model to whiten the residual and make it approximately a standard Gaussian. The method is designed to be a white box approach, finding a function that invertibly maps vector timeseries data to independent and identically distributed standard normal variables. It is inspired by recent work on the trade-off of fit versus roughness in stratified Gaussian models and convex optimization-based signal decomposition. The authors present a novel approach to modeling and analyzing fleets of photovoltaic systems using a smooth periodic Gaussian copula transform. They demonstrate the effectiveness of their method by applying it to real-world PV data, showcasing its adaptability and accuracy in capturing the time-varying nature of solar irradiance and the correlation between systems. Estimated quantiles for each system, obtained using the time-aware copula transform, exhibit distinct characteristics and collapse to zero at night as expected. The authors also employ an AR model with memory m equals 3. Revealing that previous values for each system play a larger role in predicting the current value than previous values of other systems, although non-zero off-diagonal elements indicate inter-system dependencies. Residuals of the AR model are fit to a smoothly varying periodic Gaussian distribution, with means being small and standard deviations varying considerably across systems and time of day. Correlations of selected pairs of residuals are around 30%. With physically proximal systems being more highly correlated. The authors illustrate the applications of their model, including generating simulated data, computing conditional marginal quantiles, and detecting anomalies. They demonstrate anomaly detection on System 2, introducing synthetic anomalies and detecting all artificial anomalies with a threshold E equals 0.01, with 3 false positives. The proposed method has potential applications in improving the efficiency of solar energy systems, particularly in the context of grid integration and energy storage. The authors highlight the importance of accurate forecasting in solar energy systems and the need for statistical models that can effectively capture the variability of solar irradiance. They discuss the use of quantile regression to estimate conditional quantiles of the clear sky index and the potential for scaling up their approach to larger problems and applying it to other types of renewable energy systems. Future research directions include integrating additional variables and developing more sophisticated statistical models to capture complex environmental interactions and PV system performance.